At 10:01 in the morning, Qantas Flight 32 is climbing away from Singapore when two almost simultaneous bangs stare through the aircraft. The crew sees a warning for engine number 2. For a few seconds, this still looks like an engine problem. Then the messages start arriving. Warnings begin appearing across the hydraulic, electrical, flight control, braking, fuel, and landing gear systems. Auto thrust and auto land are also affected. One failure after another, across systems that were designed to be independent. The A380 has 4 engines and layers of redundancy. Losing one engine should be manageable, and within minutes, the failed engine will become the least complicated problem on the aircraft. But this is not a normal engine failure. Something has exploded with enough energy to punch through the wing, sever wiring, rupture fuel systems, and disable multiple backups at the same time. There are 169 people on board. And before this aircraft can land, the pilots first have to answer a much more basic question. What aircraft do they actually have left? Qantas Flight 32 is an Airbus A380, registration VHOQA, flying from Singapore to Sydney on the 4th of November 2010. There are 240 passengers and 29 crew on board. And unusually, 5 pilots are on the flight deck. The flight includes a row check, so alongside the operating captain, first officer and second officer are 2 additional check captains. That detail will become extremely important. At 1:57 UTC, Flight 32 departs Singapore Changi Airport from runway 20 center. The takeoff is normal. The landing gear comes up, the flaps retract, the A380 begins climbing toward cruise altitude. A few minutes later, while passing roughly 7,000 feet at about 250 knots, the calm ends. 2 loud bangs are heard almost together. Passengers on the left side can see that something is badly wrong with the inboard engine. In the cockpit, the electronic centralized aircraft monitor, the ECAM, begins reporting an overheat on engine number 2. The crew reduces the thrust and works the displayed procedure. Then the warning briefly changes to an engine fire. The pilots proceed to shut the engine down. But shutting down engine number 2 does not stop the emergency. It reveals it. Inside the Rolls-Royce Trent 900 engine is a small oil feed stub pipe. Investigators would eventually discover that some of these pipes had been manufactured with a wall thinner than the design required. On the engine fitted to Flight 32, that reduced wall thickness allowed a fatigue crack to grow. Oil escaped from the cracked pipe and ignited inside the engine. The fire weakened part of the intermediate pressure turbine structure. The turbine disc separated from its drive system, accelerated beyond the speed it was designed to survive, and burst. That distinction matters. Jet engines are designed to contain many internal failures, but an uncontained rotor failure means high energy fragments escape the engine case. On Flight 32, pieces of the turbine disc left engine number 2 like shrapnel. A large fragment struck the left wing, penetrating the leading edge, passing through the front spar and into the fuel tank before exiting through the upper wing skin. Other fragments struck the wing-to-body fairing and the aircraft's internal wiring roots. This is where a single engine failure becomes an aircraft-wide systems emergency. The A380's redundancy still exists in theory, but the debris has physically cut through some of the routes that make that redundancy work. In the cockpit, the ECAM begins building a list that seems to have no end. The crew later record dozens of individual alerts, with many more subsystem failures behind them. Engine numbers 1 and 4 are operating in degraded modes. Engine 3 is operating in an alternate mode after one of the procedures is actioned. The green hydraulic system reports low pressure and low fluid level. The yellow hydraulic system reports pump problems. 2 AC electrical buses are lost. The flight controls revert to alternate law, reducing some of the normal protections. The leading edge slats are unavailable. Aileron control is only partial and spoiler control is reduced. There are warnings involving the brakes, fuel system, landing gear, air data, and anti-ice systems. Auto thrust is gone, auto land is gone, and fuel is leaking from the damaged left wing. This is not simply a long checklist. Each alert changes the meaning of the next one. A braking failure matters more because the aircraft is heavy. The missing slats matter more because they raise the landing speed. The fuel transfer failures matter more because fuel is leaking from only one side, changing the aircraft's balance. And the loss of multiple electrical and hydraulic functions makes it harder to know which indications can still be trusted. The crew informs Singapore Air Traffic Control and enters a hoarding pattern. The instinct in an emergency is often to land as soon as possible. Flight 32 does something that can sound counterintuitive. It stays airborne. The reason is simple. The aircraft is still controllable, and the crew does not yet understand all of the damage. Landing immediately would mean committing to an approach before they know the aircraft's configuration, braking capability, control authority, or landing distance. So, they buy time. For around 50 minutes, the pilots work through the initial ECAM procedures. The extra flight crew on the flight deck becomes a major resource. Tasks can be divided. One person can fly, another can work checklists. Others can monitor systems, calculate performance, communicate, and challenge assumptions. The problem is no longer just following instructions on a screen. Some of the instructions themselves become questionable because the aircraft's fuel and sensor information is damaged. The crew sees multiple fuel messages and decides not to continue transferring fuel when they cannot be confident about the integrity of the system. The fuel jettison system is unavailable. That creates the next problem. An A380 that has just taken off for Sydney is carrying far more fuel than it would normally carry at landing. Flight 32 is roughly 50 tons above its maximum landing weight. They cannot simply dump the excess fuel. And because fuel is leaking from the left wing while transfer capability is degraded, the crew also has to watch the aircraft's center of gravity and lateral balance. They are not trying to restore the A380 to normal. That is no longer realistic. They are trying to build a reliable picture of what still works. That change in mindset is one of the most important moments in the entire flight. Eventually, the problem becomes brutally specific. Can this aircraft stop on the runway at Singapore? The normal landing configuration is gone. The leading edge legs are inoperative, so the aircraft must approach faster. Braking capability is reduced. Some spoilers are unavailable. At least one thrust reverser will not be available in the normal way. And the aircraft is about 50 tons overweight. The crew enters the failures into the A380's landing distance performance application. The first result is not comforting. The computer cannot calculate the landing distance with the full set of abnormal conditions entered. So the crew examines the inputs carefully. Because Singapore is dry, conditions relevant only to a wet runway can be removed from the calculation. After simplifying the inputs to those that actually apply, the system finally returns a landing solution. The expected touchdown speed is around 165 knots, roughly 35 knots faster than a normal approach. And the calculated stopping margin is tiny. Only around 100 meters on a runway about 4 kilometers long. That number is not a guarantee. It is a plan built from damaged system information. Before committing to the landing, the crew conducts controllability checks, essentially testing the aircraft in the configuration and speed range and the speed range they expect to use on approach. They want to know how the specific damaged aircraft behaves before they descend into a position where there is no time left to learn. When the decision is finally made to return, the landing gear cannot simply be treated as a routine extension. The crew uses the alternate gravity extension system and verifies that the available indication shows the gear down. Auto thrust is unavailable, so thrust has to be managed manually. With multiple engines integrated or alternate modes, the crew limits how aggressively some of them are used and manages speed using the engine they trust most. The A380 lines up with runway 20 center at NG. It is heavy. It is fast. It has reduced lift devices, degraded braking, reduced flight control capability, fuel leaking from the left wing, and a damaged network of systems behind the cockpit displays. During the final approach, recorded data later shows a low energy warning at about 362 feet radio altitude. Then, just before touchdown, a stall warning is recorded at only a few feet above the runway. At 3:46 and 47 seconds UTC, the main landing gear touches runway 20 center. Maximum braking follows almost immediately. There is no dramatic last-second maneuver. Just a very large, badly damaged aircraft using almost everything it has left to stop. At roughly 3:48 UTC, Flight 32 comes to a halt on the runway. All 469 people on board are alive. But the emergency is still not over. After landing, the crew shuts down engines 3 and 4. Then they try to shut down engine number 1, the outer engine on the same damaged left wing. It keeps running. The normal engine master switch does not stop it. The fire controls do not stop it. The reason is another consequence of the original turbine disk explosion. Debris is severed wiring associated with the fuel isolation system for engine number 1. The cockpit can command the engine to shut down, but the damaged aircraft cannot carry that command all the way to the valve that cuts the fuel. At the same time, fuel is still leaking from the left wing and black temperatures are a concern. That combination makes an immediate evacuation a complicated decision. Emergency services apply foam beneath the leaking wing. Passengers are kept on board while stairs and buses are arranged on the right side, away from the running engine and the damaged, leaking left wing. Disembarkation begins around 50 minutes after landing and takes about another hour. The final passengers leave safely. Engine number 1, however, continues running. Multiple attempts by the crew, engineers, and emergency services fail to stop it. Eventually, around 3 hours after landing, firefighters pump foam directly into the engine inlet and finally shut it down. The same explosion that had happened minutes after takeoff was still dictating events on the ground hours later. The Australian Transport Safety Bureau traces the initiating failure back to manufacturing. The oil feed stub pipe in the high pressure and intermediate pressure bearing support assembly had a thin wall section that did not conform to the design specification. A fatigue crack formed. Oil leaked. The oil ignited. The internal fire weakened the turbine structure. The intermediate pressure turbine disc separated, oversped, and burst. Investigators also found something broader than a defective pipe. The event exposed weaknesses in manufacturing quality controls and in the assumptions used to model the consequences of an uncontained rotor failure. The damage to VHOQA exceeded the modeling used in the aircraft's safety analysis for this kind of event. Rolls-Royce introduced inspections and manufacturing change. A revised engine control software standard also added intermediate pressure turbine overspeed protection, intended to shut the engine down before a similar disk could reach burst speed. Regulators were also asked to review the lessons from the airframe damage when considering future certification guidance. Qantas Flight 32 is often remembered as the day an A380 engine exploded and the pilots landed the aircraft safely. But that description misses the real story. The difficult part was not losing one engine. Modern airliners are built to survive that. The difficult part was that a single physical event cut across systems that were supposed to provide backups for one another. The crew could not solve the emergency by memorizing one checklist. They had to slow the problem down, divide the workload, question unreliable information, test the aircraft they actually had, and make a landing plan from incomplete data. The aircraft survived because redundancy existed. The flight survived because the crew understood that redundancy had limits. One cracked oil pipe began the chain. The evidence of everything that followed was written across an engine, a wing, hundreds of system messages, and a 4-kilometer runway in Singapore. Every flight leaves evidence. This is Flight Trace.